equal sleep. Anyway, 12. So we are now into the last part of this course, which is the chapter 5. Chapter 5 is looking into the memory organization, looking more into the, of course, the performance evaluation of the memory by itself and the memory as a part of the system. And we say look into the memory evaluation, that meaning we are looking into like CPI, what is the effect of the bandwidths and the memory accessibility on the whole entire system and the whole entire performance. Everybody know that memory, it's a wide word. It's like a big branch. It's not just like memory and that's it. There is memory called cache. There is memory, which is the normal memory, which is a DRAM technology. There is USB stick. There is NVMe memory, whatever. There is SSD, still memory. All of those are memory. Any type of storage is considered a memory. But then the name and the category, it's actually changed based on the configuration, based on the technology, and based on the needs and application as well. Okay. So normally the computer, if you look at it, it's look like what? It's a box, have bunch of peripherals and a computation element, and then storing while you're doing the process, because you don't have the infinity elements to do the processes. So the processor, we already studied the arithmetic operations based on the data format in chapter 3. We studied the hierarchy of how can you access the stack from the software level on chapter 2, and we studied the internal blocks, the activity level and the power level based on an instruction format for the chapter 4, and also the implementation style when we look to the single cycle versus multi cycles or the pipeline implementations. And now we are looking into the memory. As I said, memory can be cache, can be main memory, can be secondary memory, which is going to be the driver with the drive, and that driver can be like the spinning needle, or it can be the SSD, or it can be NVMe, PCIe, or whatever versions we have these days. And then we need to communicate with our computers, so the devices or the peripherals will be counted as input and output devices like keyboard, mouse, scanner, printer, microphone, and all these things. Sounds good? Hello?
Yeah, sounds good.
Super. Now, we need to start thinking about, as what is the outcome? What is the target of this course? Somebody can tell me what is exactly we are trying to do in this course. We are studying what?
Architecture.
Yes, but what is the most important thing in this course?
Performance evaluation?
Exactly. We are learning how to evaluate anything. We are learning how to evaluate processor versus processor, memory versus memory, system versus system. So we are not learning specifically architecture, because if I look to architecture, if I'm gonna make a course for architecture, this course will not be just talking about risk. My course will be talking about risk versus RISC-V versus CISC versus VLIW versus Harvard Newman for both of them. And architecture, then this course, it has to be the new course for the architecture. It has to be completely hardware or completely software, or something in the middle, which is the firmware. But the course we are taking here as an elective, it's more focused on the performance evaluation. And we are taking one of the use case of the architecture, so we can apply all of the performance evaluation on it, which is a risk architecture. And we are getting into more narrow, and we are picking one of the use case processors using the risk architecture, which is MEPS, to be like a toy or like a test bed or whatever. We can start applying all our knowledge and whatever we learn about performance evaluation on it. We have to put this in our head every time somebody asks you what is exactly you learned out of this 4300 performance evaluation. Of How do you know to make a performance evaluation? And we apply it on a certain architecture. Sounds good? Now, if I start looking into the processor and the memory, basically memory, they have their own bunch of researchers, bunch of like designers, you know, infinity number of like an army of people who are working in memory design, memory verification, memory testing, memory evaluation and benchmarking. And there is another people who are more dedicated their life and their like, you know, workforce towards building processors, shrinking transistor to make more cores, looking into the architecture, whether that, you know, I need a memory in the middle, like a cache or whatever, looking into the arithmetic operation, how can I speed up the addition versus subtraction for the floating point versus the integer, right? So if I start making comparison from the performance perspective between the people, the army of processors versus the army of memory, I will find a huge gap from in what perspective? Performance. So if you look from the time scale here in front of you from 1980 to 2010, and by the way, the gap still exists even for 2021, you will find out that, you know, they started together because, you know, there is no computer without memory and processor, right? Like human, I have a set of cells, neurons are acting as a memory, while the others acting as a what? Computation elements, CPUs, whatever, ALU, whatever you call them, right? They started together, and the gap started from 1985 to get what? Wider, until they came into a point between 2000 and 2005, that gap was like, you know, 1.2 per year, which is a big thing. And somebody will tell me, from your point of view, why there is a big gap? Just like think, why there is a gap between the processor versus memory in terms of performance evaluation or even performance in general? Try to think with me.
Maybe it's because on processors, you can just add more cores. And with memory, it's not that simple.
That's actually really good. Also, if you look to the trend, you will find people keep adding. Yeah, Grant, yes. So, and you know, and Rohit, both of you are correct. Basically, the processors, the whole trick, shrink transistor, have more transistor on the chip, add more cores on the chip. Then, you know, look into the architecture level, or make more thread, more cores running in parallel, serialize in the middle, you know, put like external set of registers in the middle to exchange data between cores and all of these things. But memory, there are two directions we have to focus on, right? What is the first direction? The density. How much information I can locate in the memory. So there is one direction, which is make the memory huge. It will store more data. Then the second challenge, if I make it huge, how I'm gonna search inside the memory to pick up the data or to locate data coming from the processor. That means it's like a search engine, right? Because the memory from the naive perspective, it looked like what? A big table, and you are just putting your finger as a pointer to point to which row you want. Whether that you're gonna pick data out of it or you're gonna locate data there. Do you guys agree? Definitely, the searching inside the memory to pick up the right data, or you know, to locate the right data, the ultimate goal for us to do it, what? To do it in 0 seconds, right? But there is a physical barrier. This physical barrier, we define it as a what? In terms of performance metrics, bandwidths. Bandwidths. We're gonna talk about this later, but you know, I just want to go through everything from this perspective. Bandwidths. So what is bandwidth from your point of view? Bandwidth is mean how much amount of data per second I can request the memory to locate inside the memory or to bring it to me as a processor so I can do my process. Of course, if I start comparing between memory A and memory B, I will think that the memory will give me more data per second that will be more appreciated than a huge memory that will be storing data. Maybe there is another application is really hungry for storing data, like for instance AI. And AI, while I'm training, I need to store weights and then pick it up and then iterate again and then store it and pick it up and then iterate and so on and so on. So that's actually a kind of like a very, very intense memory needs in terms of the storage perspective. Maybe the speed of the training, it can hurt because end of the day you have to wait for like a couple of days and hours and day and night until the steady state weights of the neurons will come out. Then you can use it as an inference and then start using in your application. To summarize whatever I talked about now, yes, memory is doing memory architect people doing a great job in terms of make it more dense, as you guys have seen before, right? Have you guys watched this photos about the old version of IBM machine? It was building and 8 megabits whatever size wise, and after that they shrink it a little bit, they start building this SSD, what's called SSD card and NVMe, which is really tiny and it has more data. Of course, technology will be playing a role here, whether it can be static or dynamic, and we're going to talk about that later on. We need to see, okay, we figure out there is a problem, there is a gap between of the processor and the memory. Do you guys agree? Now we need to see the effect of this gap on the whole entire system when it will be running a certain application. Because end of the day, I'm looking to the whole entire system, which is running something, right? So the impact on performance, we need example to show us this impact. Without the impact, I can tell you a story. Imagine the following. I have, for instance, invited Jonathan and Mark and Daniel and Rohit and Jean for dinner in my house. Then, I went to the kitchen and then, I cooked for them fancy. Yes, and Lance is happy. Okay, we're gonna bring Lance also. Okay, anyway, so, I made a pizza. Then, I went to the kitchen and I made the first pizza, right? Then I just like, I put it on the middle of the table, dining table, and you guys started eating. So let's imagine that, the amount of food I made wasn't enough for you guys. So you guys told me, oh, we would like to have more. Then I went back to the kitchen and then I started cooking more and then I bring it to you. While I went to the kitchen, you guys were doing what? You were not eating. Maybe you're talking or something, but you're not eating. So you have been what? Idle. So of course, if the amount of data per second is not enough as the processor is fast, I'm gonna be idle. The processor will be idle. It will be waiting for more data to come from the memory. So of course, the performance will be hurted by the performance evaluation of the memory. Really bad. Let's see how it's bad based on this example we have in front of us. Suppose that we have a processor, the crystal of the processor, that means the one is generating clock, is running 200 megahertz. 200 megahertz based on whatever we learn, frequency, flip it, it's gonna be 5 nanoseconds per cycle. And this processor, the number of cycles per instruction, CPI, is 1.1. Sounds good? Then I'm running a certain algorithm, benchmark. This benchmark, 50% of the benchmark is communicating with who? Doing processing computationally. So that means arithmetic logic, stuff like that. 50% of the whole entire benchmark talking to the ALU. While 30% of the whole entire benchmark of the processes is actually for communicating whether that I'm loading data from the memory or locating or storing data into the memory. And the rest of the instructions were were classified or categorized as a 20% for control purposes, like you jump or you're branching and stuff like that. Suppose that 10% of the memory operation is getting 50 cycle miss penalty. What does it mean, miss penalty? Imagine the following. Imagine that I requested an X order from the memory. The memory didn't give it to me on time. That's called what? Miss penalty. So the miss penalty for me, 10%. Every time it's taken what? 50 cycles. Example for the miss penalty, we're gonna make it easy. Memory in general is hierarchy. You guys know that, right? So the processor has a cache, the cache connected to the main memory connected to the SSD card or the drive, whatever, spinning drive, and the spinning drive connected to your whatever. Then the processor went to talk to the cache and say, cache, give me location 500. Cache controller starts searching, didn't find 500. So what he gonna say? He has to report to the processor, say that I didn't find 500. I'm talking to the main memory to give me the 500. That's miss penalty because I didn't find the 500. Make sense? So based on this, we're gonna recalculate the CPI of the whole entire system involving the miss penalty. So how is this? It's a cumulative thing. So the idle CPI, the processor is doing by himself while communicating with the memory. So they're gonna be adding the stall. That means how much time this memory will stop while bringing me data if the miss penalty happens. So in that case, it's gonna be 1.1 plus, we said 30%, it's gonna be load and store. So 0.3 times the 10% times the 50 cycles I have. So in total, what happened? The CPI was 1.1, it turned to be what? 2.6. What does it mean? It means really huge for us as a performance evaluation people. It means that this processor will be 58% of the time doing nothing. Would you imagine that? 58% of the whole entire of the program running, this processor will be just waiting like this until the memory will satisfy the demand of the processor. Let's see. Can you repeat what a miss penalty is? Sure. Again, so let's say that Lance, I came to your house, I knocked the door and I said, Lance, can you please give me the Hennessy book? Then what happened? The day before, actually you give this book to Jean. So you will say, Professor, I cannot give you the book. 1 second. Then you will have a phone call to Jean. Hey, Jean, can you please give me the book? I will reply back to her, yes. Then what happened? The process of Jean and you talking to each other to bring me the book, it's actually what? Penalty. That means, I'm doing nothing. So I am actually what? Adding on this and penalty. That means, I have to wait you more. Waiting you more, that means I'm not going to finish my work fast.
Wait, so this means the processor is the idle one, right?
Yes.
Okay.
Because the processor is just like, I need 500. Give me 500 so I can resume.
Okay.
That makes sense? Now, there is a big problem. Yes, this example, with the 50 and 10, show us something. But what about if we slightly change the miss rate? Look at this really bad thing. I change the miss rate by 1%. 1%, that's gonna give additionally half cycle on the CPI. So every 1%, half cycle. So that's actually gonna hurt really bad number of cycles per instruction. That will make this processor what? Completely jailed. Cannot do that much of the work, and this 58% will jump really bad. So that show you the meaning of to make this memory strong, fast, dense, and replying to all the requests of the processor on time based on a very strong pipes of the bandwidths. This example is very important. I hope that you guys fully understand the story of the miss penalty. And I hope also you guys understood that, the gap itself is causing what? Idle in the processor of processing data in general. Now we're gonna start talking about memory. We start talking about the biggest or small of the memory, how it works, and the technology that's covering the memory architecture. So there is something that we learned before. If you have a huge container, that will make me finish everything fast, right? That will bring everything here nearby the campus. I will get everything done and I'll finish. So the illusion of loss, fast, cheap memory, it's something as a follow. People, when they said, large memory, in reality is actually what? A slow memory. And the fast memory is a small memory. Why? If I give you a table with 5 names and I tell you, give me the location number 4, your eyes will not take that much time to find location number 4. While when I give you a table of 1 million names written in the table as a row based, and I ask you to give me the location 780,000, then you're gonna take your time until you will pick it up for me, right? So that's actually too much effort you're gonna do. To solve this problem, they build the hierarchy. They build a small memory close to the processor. They call it cache, and they get it more bigger and bigger and bigger and bigger. And later on, you guys will hear about something called L2 and L3 caches. And I'm not sure if you guys have heard about this before or not. Have you guys heard about L2 and L3? Yes, so L2, L3, and even L1 and L whatever 4, it's a type of cache getting smaller close to the processor, getting bigger when it's getting far from the processor. It is something as we did, do you remember, with what? With GPR, general purpose registers. GPR, why is not like 1 million registers? Because at the end of the day, gonna be act like a memory. I want something then is, yeah. So basically, larger it should be far from the CPU, smaller should be closer to the CPU. That's true. I think Rohit asking me questions before. Let me see what he was asking for. So our most computer today also waiting most of the time for the memory. Yes, it's infinity. It's an infinity war between of the memory people and the processor people. The only people who will solve this problem, the people who work in quantum. You know why? Because in quantum, they're gonna use the entanglement. And I think I told you guys about entanglement before, right? In entanglement, here is my memory, here is the processor. And then, if I put them in entanglement, whatever inside the memory, it will be accessed by the processor in 0 time. Because those two guys consider like, they are still the same entity. You know what I mean? So then, bandwidth here is gonna be like infinity. So I can request any type of data, amount of data I want at any time I want in 0 time. That will be using the superposition, yes. Yes. So superposition is a different story, but it's using it. So, London, superposition is the following, we are no longer 0 and 1, right? You know what we are? We are basically like this. We are in a sphere. So in the sphere, I can go here and go like this. This is a state, 0 and 1. So before, my bits, my 1 bit is 0 or 1. Do you agree? So here is basically what? A state 0 and 1. Here is a state 0 and 1. Here is a state 0 and 1. Here is a state 0 and 1. But then, since I already have a spherical coordinates, I can actually have something between 0 and 1. Do you agree? Based on the what's called the angle, right? That's actually called superposition. That means what? I'm 0 and 1 at the same time. You get my point? So in that case, I can actually process something new, which is 0, in 0 and 1, something new, I can do something in the middle. Or even, something between 0 and 1, there is infinity, because, the scale will be changed by the angle, so I can do a lot of process during that. And then also I have infinity states, 0 and 1 by itself here. So, you know, 1 qubit can be like a huge supercomputer maybe. The entanglement is different story. The entanglement, that means it's synchronized, you know what I mean? So that means, you know, if I have a particle here and particle here, this particle in the beginning of the universe and this particle in the end of the universe, I entangle them, that means they are what, synchronized. So if this one is spent like this in this direction, this one will go exactly like this direction. If this one is spent in that direction, automatically this will be in this direction. And this will happen in what? T equals 0. T equals 0, period. So imagine that, you know, I'm entangled with YouTube. What will happen? I don't need to go ahead, you know, that would be exactly, that is extremely in a way that, you know, there is nothing, there is no buffering, nothing, right? Another story I will ask you, what is the ultimate goal for humans in computer architecture? Is to make the computer not even using peripherals. Why I have to have a keyboard, I have to have mouse, all of this is too much. You know what I mean? What I can do, yeah, exactly, Neuralink. So, you know, I will just sit like this and I say, you know, I'm not gonna even say it, you know, I will just like think about, you know, a song. Then, you know, that song will be coming in front of me. Then I can use what's called the virtual reality or something. I don't need even a screen. Then I would be like, oh, I see everything. Then I will be in a quantum order. Yes, yes, you can order dominoes without saying anything. And you know, dominoes will be entangled with you, so it will come to you in t is equals 0. So, you know, because, you know, they're gonna be also the oven working in entanglement that will be actually cooking everything in t equals 0. So you're not gonna, as human, you're not gonna even, you know, waste energy, you know, for like, you know, moving and going, you know, it's a big mess. Anyway, so let's go get out of this and, you know, move to the rest of the lecture. So anyway, now, since we already learned that, you know, there is something called small memory and something called large memory, now we have to sort them in a very nice way. In theory, you know, the processor is a high demander. It's demanding a lot. So we have to put something fast close to the processor that will be what satisfying the demands of the processor. You guys agree? In that case, we need a smaller memory close to the processor, and the biggest memory would be far from the processor. Then, you know, that hierarchy, it will be what make the memory more efficient, and we call this memory organization. So how to create a large and a cheap and fast memory? You have to make hierarchy. And also in some of the stages, you're gonna do what? Parallelism. So you're gonna make like multi-segments of the memory. Accessibility is gonna be in parallel, for instance. So hierarchy, that means you're gonna make a hierarchy, and also parallel in the middles that will be giving you as an architecture large and a cheap and fast. And that's basically what we have, as you can see. So you don't need to think too much. Computer, memory, and computation. Then they will just give names here. You know, they will give you name of this and they call it GPR. They will give you a name of this and they will call it cache. They will give you a name of this, they call it memory. They will give you a name here, they call it SSD. They will give you a name here, they will call it NVMe. They will give you a name here, they will call it CD-ROM, and so on and so on. But all of them are called what? Memory. Make sense? Anyway, now we need, you know, this is computer science part. That's not ECE, by the way, these slides. But I want you to think about it, it's very fun. There is something called locality. So the elements, the one we cascaded like in a hierarchy nearby each other, they have to fulfill some principle. What is this? I will tell you. Imagine I have an open book exam. I have an what? Open book exam. Sounds good? This open book exam, you know, in the electromagnetic field. Then what is my strategy to prepare for this exam? You will go to the library, and when you will go to the library, you will go to the section of the electromagnetic field before the rest of the class members will be there, and you will take all of the books, and you will just left it with you and go back to your home, study, and even put them in front of you so you know exactly what exactly you will need in case of emergency in the exam to pick it up. No, you don't need to burn anything. Anyway, so in that case, you got all of the possible knowledge you can ever have, right? In front of you. Accessibility is a different story. That's called what? Locality in a space. So my memory nearby the processor in general, it has to be fulfilled that. So let's say that, I ask it for location number 500. It's better for me to bring 505 and 510, the friend of the 500 together, and I put them in the cache close to the processor because I might need them. In the top of that, there is something called locality in time. What is locality in time? If you wrote a for loop, the for loop, you set up the indices, right? You make I equals 0, and then, you would say that up to what, and then, you start incrementing by the step 1 or 2 or 3 or 4, right? Then, you will have a body of the for loop, and then, you will make the close of the for loop based on the language you're using. Do you guys agree? End of the day, the whole entire thing is memory. So my question to you, if you are starting now the for loop, that body of the for loop, are you gonna put it in the far from the processor? Are you gonna put it close to the processor? You're gonna put it close to the processor, because by the end of the finish loop, you're gonna need to go back to access the second loop and the third loop and the fourth loop. So this is actually locality in time. It's a time accessed recently are likely to be accessed again soon. Example, instructions in loop. And the locality in space, it's items near those accessed recently are most likely they're gonna be accessed soon somehow. An example for this, if you have an array of data, and I access element number 5, I'm gonna just go ahead and bring element number 5 and I put it in the cache? Nope. I'll bring the whole entire array, because most likely I will need element number 7 later on, element number 17 or whatever. So possibility for exam from the 3 of whatever, how many slides we talked about, right? You need to know there is a gap in terms of performance, gap in terms of technology for memory and the processors. You need to know the side effect of the gap, and numerically we calculated with the example, and then we start talking about how can we build the best memory organization based on the information we know that smaller is faster, bigger takes some time, it's gonna be slower, and we build the hierarchy based on the hierarchy plus variance. Right? Then the locality, and it can come into like a true or false questions or multiple choice. Any questions so far? Hello.
All good.
Perfect. Anyway, so whatever I said is written, So a structure that uses multiple level of memories, because memory passing to memory. And don't forget, those guys are not talking bypassing each other. Those guys are using the indirection. What does it mean, indirection? That means the processor, he doesn't know that, there is other memory in the system. The only thing for the processor, he knows there is something called cache. But cache, no, there is a processor, and also no, there is main memory. Main memory, no, there is actually cache, and no, the hard drive. But main memory doesn't know there is actually core processor. Make sense? And you move forward and move forward and move forward. That's called indirections. In computer science, they call it indirection. So you are trying to simplify the communication. I cannot, for instance, come and say main memory, go talk to the processor. That will be a chaos. Make sense? Of course, if I would like to build a small memory, it's gonna be expensive, by the way. We're gonna know why expensive in the later slides, but it's a smaller, but it's very expensive. So for instance, do you know why the processor is very pricey? The price of the processor coming from the cache. Do you know that? So when they come and say, oh, i9, $1,500, you'll say, what? You know, they didn't like speed the clock rate really high or something versus i5, for instance, right? Or i7 or whatever. No, but you know, the devil in details. Oh, you know, the memory is bigger, or maybe the reaction or the accessibility of the cache is faster than the one in i5. So that's why, you know, the price will just go significantly up. Oh, by the way, I'm not sure if you guys are following the news. Do you know that NVIDIA also is designing CPU? Have you guys heard about that? That will be a big mess for Intel. I think so. I think Intel people now is like, you know, getting mad. Yes. So, you know, imagine people work in GPU and they know what is the fast thing in the GPU. Now they are going into the CPU. That's, you know, the stock market for Intel gonna be like in deep trouble. Yeah, no, but you know, Tesla, when they're gonna go do GPU, they're gonna do it for their own specific processes. But let's see. Anyway, so now we need to tie the missing ring about memory and technology, because end of the day, all of these guys are hosted on what? Semiconductor, right? Silicon. So the technology used for memories are different. So for instance, if I start looking, this study is like 2012, which is fine, you know, still valid. There is NVMe and stuff like that. I can add it here, you know, I can roughly tell you the response time. Anyway, so there is something called SRAM. SRAM. SRAM is standing for Static Random Access Memory. Why is it called Static Random Access Memory? Because the cell, it had been built on the silicon for hosting data bit is based on what? Transistors. CMOS technology. Roughly, they say, you know, 6 to 8 transistors will be used to host 1 bit. That's why the price will be really expensive. So you can see that, you know, look, the cache, $500 per GB. Gigabytes, $500 to $1,000. But look at the response time. So when I, as a processor, request something, it will give it to me within 0.5 nanosecond to 2.5 nanosecond. You will not feel it, right? The one is bigger, dense, a number of elements can host data is the DRAM, which is the main memory we are using these days. When you say I have 32 gig, I have 64 gig, I have 128 gig, right? And you know, you will look into your motherboard and say, oh, my motherboard can just take 16 gig. Do you remember most of the laptops, right? The normal laptops, they will just say 16 gig memory, right? I mean, I heard now these days, you know, there's 52 gig, but you know, of course, the price will just go up because the motherboard, you know, accessibility, stuff like that will be more challenging. Anyway, so DRAM, the cell used for storing and hosting the data, guess what? Capacitor. It is a capacitor. But somebody will tell me, but this is semiconductor. Why you are telling us it's a capacitor? It's still a transistor, by the way. Because, you know, I'm not sure how many of you heard about some topic called VLSI. Have you heard about it? So in the transistor, if you look at it, the transistor look like that. You know, I have here, you know, N, I have here N, I have here P, that's called substrate. Substrate. And then, you know, I have here multiple layers, and here is this is my channel, and the channel will be moving from here to here, and here's the source, and here's the drain, and here's metal oxide, and there's some isolation, and here's the gate. If you put the transistor in a specific area of the characteristic, you know what is characteristic? It's basically this is the characteristic between the volt and the current. So, you know, like this. Here is the saturation. Here is kind of like ramp or the transitions. Here is the cutoff. If you are in a cutoff, then either that I'm holding the charge or releasing a charge. So this guy no longer will look like a transistor. It will act as a capacitor built using transistor. So anyway, back to the point, DRAM is fancy. You can host a lot of data there, and also the price per the gigabyte is nothing. It's like a $10. Look. But look at the response time. I ask for something, it will come back to me as a processor from 50 nanoseconds to 70 nanoseconds. Huge, huge difference versus SRAM, right? Later, I will tell you what is the reason, but the reason is really, really funny. Okay, anyway, now there is a flash memory. Everybody know the flash memory, right? Flash memory, more dense, more, stuff you can put it in the stick, whatever. That will be taken 5 microsecond to 50 microsecond to satisfy the requirement I'm looking for. But of course, the price is cheap. Then, the magnetic disk. Look, this guy is really poor, right? It takes 5 milliseconds to 20 milliseconds, 5 to 20 milliseconds to reply back to me with my request. And the price will be cheaper and cheaper and cheaper. So we need to know the details why SRAM faster than DRAM. And you're gonna also notice something. DRAM is more dense than SRAM. That means DRAMs can be bigger in size than SRAM. And of course, the price will be affordable compared to the SRAM. And you have also to know that SRAM is located where? On the cache, because it's building the cache. That's why the processor is expensive. This is already replicated. I just told you about it. I just brought it for you, but that's fine. Anyway, and also this is about the locality, and we talked about this, right? We need now to start using the locality, applying the locality we learned, which is a special locality and time locality, based on the knowledge we learned about DRAM and SRAM, right? So we're gonna put the SRAM near the processor. We're gonna put the DRAM. We're gonna put here the magnetic hard drive or the SSD, and then SSD, NVMe, sorry, NVMe, SSD, and then magnetic and so on. Right, and then we're gonna start applying the locality based on oh, I will take a copy of my data from main memory. I will host it on the cache. And then if I want something from the magnetic, I can put it in the memory. And with following the locality, and then I will move to the cache and so on. There is something, it's called TLB. TLB. I'm not gonna go too much on it, but this can be covered on a course I teach. It's called 5850, computer organization. That's actually for the master degree. But in general, what is TLB? It's like a buffer. The buffer acts like a cache, but it's not cache. Something inside the memory, acting like a cache. And that will help you with the virtual memory. We'll talk about it later if we have time. In terms of the principles and the probability for getting data out of the memory and the reasonable time or instant of time, there is some statistical modeling. And I know all of you got the 3715, right? I don't want to put too much mass in the top of this, so we're gonna make it hard for you guys. You don't need to think about this slide too much, but later if I have time, I can go through it with some examples from the 3750 about memory architectures and memory accessibility. But for now, don't worry too much about it. Okay, now I already told you about the locality, but here is some example based on it. So temporal or time locality, here is my big memory, here is the small memory. So how can I make the temporal locality? I'm gonna start moving data and I will leave it there for the body of the for loop, and that will be working. For spatial locality, if I want an element an array hosted by the higher level of the memory, I will just completely take the whole entire array and I put it in the cache. Then I will be able to process the data here using the processor. This is like example supporting the definitions of locality. Okay, now we talked too much about memory, but we forgot our mission, which is the performance. So we start now going back onto the right track and looking into the elements inside the memory that will help me later on to define metrics for the evaluating memories. So first of all, the minimum amount of data the memory caches, as an example of the memory, can host or present, can pass it to me, is called block or line. So if some, this is very, very good set of the information in this slide for any questions I can bring to you, like multiple choice or definitions or true or false. So block or line is the minimum unit of information that's present or not present in the cache. Minimum, the bare minimum of data. Then second level of defining something about the memory is to actually evaluate the memory. So how to evaluate the memory? So imagine that I'm a processor and I asked the cache for location 500. The cache reply back and give me the data of the 500 immediately. What does it mean? Hit. I got the target. I hit the target. So hit is the appearance of the data nearby the processor, and the processor, gets happy and process the data without being altered. Who is the reverse of the hit? Miss. Miss. That means cache. Sorry, the processor asked the cache, I need location 500. Then the cache said what? There is no 500. A second to ask my neighbor. Yeah, my phone is talking to me. Anyway, so basically what happened, the cache will go to the memory and say, hi, main memory, I'm in need of the location 500. Main memory will tell him, oh, take the 500, give it to the processor. Then that will be mess. That amount of time until the 500 appeared in the cache, that will be mess, which is the reverse of hit. Of course, if you are looking for rate, let's say that, I have a big program running, right? And I start looking to the memory based on the timing. And I say, oh, I missed this time. I hit this time. Then I will start accumulating rate. Do you guys agree? And that rate is going to be the fraction of memory access found in the upper level. When I say upper level, that means, nearby the processor. Lower level, that means far from the processor. And of course, it is statistics, right? So, 100% is 1. So, miss rate is 1 minus the hit rate. Okay. And that miss penalty is basically it's a way to define how much time it took for me to get the data placed in the cache. Then, the processor will be using it. Sounds good? Hello. Super. This slide in front of you, it is repeating again the principle of locality, right? Showing you also the speed and effect. Then the slide I give you in above with how much response time and so on. Why I do this? That's for a reason, because when you are reading, maybe you will get the information by this way. Maybe you will get it graphically in that way, so that will be easy for you. So some people actually they get the information digest by graphic representation. Some people will get it based on reading representation. Some people will get it by mix of the representation, graphical and text reading representation. That's why I decide to design my slides based on that, so you guys can get benefit either way. Okay. Now, one of the most important questions. I keep saying this stage passed to this stage, this stage passed to this stage, but I never say how those guys talking to each other. What is the procedure, right? What is unit used for that? So this is very good slide to be used for a true or false or multiple choice or like fill the empty spot or whatever, right? So if I would like to look into my hierarchy and see who is controlling the data movement between the registers and the memory and the memory and the register, somebody will tell me compiler, which is mean that the programmer wrote a code will be translated by the compiler will be moving load word stored between memory and registers, right? Second, who is responsible for the data transfer between the cache and main memory and the cache? That's not controlled by us as a programmer. It's not controlled by the processor. There is a unit, hardware unit inside the processor called cache controller. It's a set of finite state machine with respect of the miss and hit and the rate of miss and hit rate, organizing the relation between the two sides of the cache, main memory and processor. So if somebody asks you which unit or what is the process of controlling the data movement between cache and main memory, you would say that will be done by the cache controller, which is defined as a hardware unit. Make sense?
Makes sense.
Super. Now, what about the disk and main memory? Disk is very far, right? Slow guy, right? 5 milliseconds, whatever, right? And 500 milliseconds, 50 milliseconds, something like that, from the slide. And the main memory, I will tell you, virtual memory. If I'm running out of space, I will go talk to the far memory, which is basically a hard drive, and I start building their allocation act as a memory, but it's not a memory. They call it virtual memory. This chapter will be focusing on the cache, main memory, virtual memory, and the effect of the performance on the three of them. And we're gonna take them one by one for the rest of the time we have for this course. How I'm gonna move between the main memory and the virtual memory. Virtual memory, the pin does not exist. It's just like, I create some section and I call it memory. There is an hardware allowing me to move between the physical and the virtual, and that's called TLB, and we already defined it up in one of the slides, if you guys remember. Right? So in general, I can give you some information about the virtual memory, and later on we can talk about it. So imagine that the processor shouldn't know that his memory, the processor shouldn't know that, the memory is limited. Because if the processor knows that memory is limited, he will be constrained. He will be like jailed. He cannot move too much. In that case, he will be afraid to do work. So the best way to do it is to actually to make the processor feel free. I have infinity storage elements. But in reality, that's not true. How we can do that? That's not really hard. The processor, for instance, is requesting location million. But this cache doesn't have million locations. It just has 5 locations. So what happened? It will go here into TLB or the table, and go here in physical, and then virtual addresses, and it will say virtual addresses, physical addresses. Then it will say location 1 million. In reality, location 5. And then I will take location 5 and give it to the processor. Did you see what I did? So it's generating this table OS, operating system. The OS is generating a table, tricking, telling the processor, imagine you have a trillion location. Then, I will go in the table and say, oh, trillion, that means location number 4. 15, location number 1. And that can be dynamically changed as security aspect is important also for computer architecture. Any question? We can, you know what, let's finish these 2 slides so we can stop on the caches, okay? So now we need to know the reason why is Sram faster than DRAM. I will tell you, because the DRAM is using capacitors. And everybody know the capacitors, if it's idle, it's gonna keep the charge forever. Do you guys agree? But you know, there is nothing idle in this life. There is nothing completely 100% fixed. Everything is relative. So in that case, you know, the dielectric here will cause some leakage over time. The charge can be flipped, and that will cause error. That's why there is error correcting mechanism inside the computer architecture. That's why there is something that's called refresh rate. What refresh rate means? So over time, if I have 5 volts here, which is representing 1 as a bit on the capacitors, that's leakage will make it what? 4.9, 4.8, until, you know, one day I will get 2.5, boom, gonna be 1.5, which is gonna be blue, some number that will turn to be 0 in the computer architecture. That means, you know, I made something wrong. So the controller of the DRAM is offering a solution. What is this called? Refresh. What refresh? I will look into the charge every couple of milliseconds. And in that case, I will lock the memory. So I will not be able to read and write. Then I will go into every single capacitor and say that, are you 5? He will say 4.9. Then I will tell him, take 0.0 to be 5. Take 0.3 to be 5. So I'm refreshing the charge to defeat the leakage. Then in that time, I'm idle. I cannot read or write. I'm locked. That's why DRAM slower than SRAM. But on the other hand, I'm using transistor per capacitor. So that means I can have more cells hosted on the chip to be acting as a memory. That's why DRAM is more dense, huge. That's why did you see the price of the GP for the DRAMs? It will be cheaper than, you know, the GP for the SRAM. Sounds good? And this is the explanation as I showed you. Now we need to start looking onto some metrics we're gonna use for the performance evaluation. So for instance, there is some performance metrics we have to look into it, like bandwidth, as I told you. Bandwidth, that means how much amount of data per second I can request and I get on time. That's called bandwidth. And of course, the bandwidth is very important when I move to architecture to the other, like IO. I'm talking to the microphone. So how much this microphone will give me per second? How much this memory will give me per second? How much the keyboard rate is coming per second and stuff like that. Then there is something also called latency. What does it mean, latency? Latency can be discussed by the 2 different subtime parameters. One is called access time, another one is called cycle time. So imagine the following. I requested location 400 from the memory. Memory replied back to me. The amount of time it takes, it's actually what? Access time. But memory in general keep requesting. So that the time between request to the other, that's actually called cycle time. So we have access time and we have cycle time. Also, the memory, like a DRAM, is a 2D dimension. In that case, if I would like to access a certain element in the 2D, I have to have accessibility in a row and column. That's called RAS and CAS. Row access strobe and the column access strobe. And every single one, it has its own time. You can accumulate it. You will get the timing model of the getting that element out of the memory. Normally the size of the DRAM versus SRAM, it takes 4 to 8 cost cycle per time, and the SRAM, it will take 8 to 16 per time. And I can say that, you know, SRAM in general, as I told you, 1 bit, it can be charging me 6 to 8 transistors, while, you know, capacitors is just like 1 transistor. I just need the metal oxide there. And now I can say that next time we're gonna stop here, and we're gonna resume our discussions on the caches on this coming Monday. If you guys have any questions, please don't hesitate to ask. I'm more than happy to assist you. It was my pleasure to talk to you guys, and I wish you the best of luck, and also, you know, a nice the rest of the day and a nice weekend as well. Any questions? Thank you, guys. God bless you, and stay safe. And that's really fun, guys. You know, I really I like this class. Okay, thank you. See you Monday. Thank you.